organized by the Department of Tripoli, Green University of Bangladesh. Our today's session will highlight the importance of compact antennas for wireless communication. We all know miniaturization of electronic devices is a blessing to the technological growth, and the researchers are struggling to make the devices more compact. We are fortunate to have Dr. MOHAMMAD NAZMUS SHAKIB sir, Assistant Professor, Department of Tripoli, Green University of Bangladesh, as our today's keynote speaker to discuss about compact antennas for wireless communication. We also have Dr. Ratil H. Ashique sir, Associate Professor, Department of Tripoli, as a session chair in charge of today's webinar. We will have a question answer session at the end of the webinar, and you can ask during that session. Now, I would like to request Dr. Ratil H. Ashique sir to say something about our webinar. Dr. Ratil H. Ashique sir, Associate Professor, Department of Tripoli, Green University of Bangladesh.
Thank you very much, Israt. Thank you, sir, Dr. Nazmus Shakib, sir. First off, I want to thank you for your time for this webinar. Definitely, it's a very commendable event that has been arranged by Tripoli Green University, and we want to really listen to our experts more in future. So compact antenna is your topic, I have seen, and I believe you are an expert on this field, and you have numerous publications, and you are a very highly cited researcher, so you know your field. But really very interesting. The compact antenna is basically now being used for various type of medical and purposes, like body-centric compact antennas. So that's a very new domain and new area for our students, and I believe there are many challenges in Bangladesh for antenna research, especially. As far as I know, there is no testing facility in any of the university in Bangladesh for antenna testing facility or antenna lab. Maybe with your help, with your initiatives, we are going to open an antenna testing lab in the University of Bangladesh and do high quality and state-of-the-art research in antenna design in future in Bangladesh, inshallah. Thank you for your time again, and I really like to see more of these webinars in future from Tripoli Green. And thanks all who has been involved in this event and has been done a lot of work to arrange this program. Thank you very much.
Thank you, sir. Thank you for being with us. So now I would like to request our keynote speaker, Dr. MOHAMMAD NAZMUS SHAKIB sir, to start his session. Dr. MOHAMMAD NAZMUS SHAKIB, Assistant Professor, Department of Tripoli, Green University of Bangladesh. Sir, I think you are muted.
Okay. Assalamu alaikum and very good morning, very good afternoon to all of you. So, am I audible?
Yes, sir.
Okay, great. Well, thank you, Dr. Ratil sir, and thank you, our MC, for giving me the opportunity to give a brief of antennas for the wireless communication. So for around 10 years, so I would like to share some of the point of views of ours that we have been developed and on this perspective. So let's start. So I'm Dr. MOHAMMAD NAZMUS SHAKIB, and I'm gonna talk today about the compact antennas for wireless communication. I'm assistant professor of Department of Tripoli, University of Bangladesh. So if some of you are from outside the university, so please visit our universities, the permanent campus that's in the Purvachal area. So you're mostly welcome to visit us. And basically, when you're about to talk about the antenna, in a broad sense, we need to talk about wireless communication technology has changed our life during the past few decades. the explosive growth of the wireless tech system, booming demand of its variety of applications, it is important to design broadband antennas to cover the wide range. Recently, wireless and wireless personal area network has gained significant interest of science and research development worldwide. In general, wireless personal area network is a type of network for interconnecting the device around the individual personal workspace in which the connections are wireless. The future wireless personal area network targets to have a seamless isolate home and business and its system. It also requires fast data storage and exchange among these devices. So before I go to antennas, let's look a preview of the people who are really need to be it's fortunate for us whom we get. So in 18th century we got Isaac Newton. In 20th century we got Albert Einstein. But however, in 19th century we got James Maxwell, but he is not as well appreciated like Isaac Newton and Albert Einstein. Basically, we are working in the field of Maxwell, which mostly focused on the electromagnetic wave. So these are the three giants who changed understanding of the law of nature. The Maxwell equation is the creator of the electromagnetic theory. He has invented around 20 equations. From that, we had the modern 4 equations, which is curl of E, divergence of D, curl of H, divergence of B. Tremendous amount of knowledge is hidden in these 4 equations. These are the 4 coupled partial derivative equations with 3 space variation and 1 time derivative. It is dependable function with space and time. So these EM theories, the amazing concept of the Maxwell's equations is that the time varying currents radiate electromagnetic wave traveling with speed of light. And if we see the radiation there, that is like it's radiating, propagating all over the place. Electromagnetic wave were discovered through the mathematical equations of Maxwell, and antennas are the most important man-made device to deal with this electromagnetic wave. So we can say the fundamental concept. So electromagnetism consists of the vector fields governed by the Maxwell equations. And the electromagnetic wave travel with the speed of light. Electromagnetic fields consist of E and H vector fields. Electromagnetic fields obey Maxwell equations, and antenna radiates and receive the electromagnetic waves. This is the fundamental concept of the electromagnetism to generate to the antennas. So as you can know about I just want to know how fast the electromagnetic wave actually travels. You know, most of us, we know the Ferrari, right? The car, the Ferrari travels 200 miles per hour. A plane travels 600 miles per hour. Sound wave, it travels 720 miles per hour. EM wave, which is the speed of light, it travels 666 million miles per hour. Just amazing.
Me, sir. Sir, sorry for interruption. We are not seeing your slides actually.
Sure.
So would you please share it again?
Because I share the screen. Can you see now?
It's okay now.
I don't know, something suddenly had happened.
Okay, sir, thank you. Please carry on.
I need to. Okay, let me share again. I think I better share directly to the slide. It's like hang. Sorry for the interruption. Maybe I slide the directly slide. Can you see now?
Yes, sir.
Yes, sir.
Yes, sir.
Can you? So as you can know, if we say that how fast the electromagnet can travel, so we know the car, the Ferrari can travel 200 miles per hour. The plane can travel 600 miles per hour. The sound wave, it travels 720 miles per hour. Imagine the electromagnetic wave, which is travel in the speed of light, which is 666 miles per hour. So we're dealing with this antenna, which is the very fast in moving. I'm not sure why this one I can't change this one. Okay. The typical antenna parameters, if we see the space, we know the antennas. Antennas comes from the load, from the impedance from one side, and the space from the other side. So what we can say that it radiates from the source antenna through the antenna to the space, or we can say it's vice versa. It's from the space to the antenna to the load. To know the radiation, the radiation it propagates, we can know the different fields with the radiation patterns, we know the directivity, the gain, and etc. Can you help me, anyone? This one I can't change. Okay, so if we look at the concept of the antennas, so the old-fashioned is like the doctor directly handling with the patients. The new era will be a different. It will be from antennas, will be go through from the portables, then it goes through the tower, from to the base stations, to the satellite, to the hospital. So it will change the concept of understanding and behavior of the nature in future. I would like to say, courtesy of this, so this one been taken from the army, one of good friends from US. So now we're going to know about the antennas. So let's say antennas, how the types of antennas. Antennas are designed implying it can be conventional antenna, slot antenna, TM horn antenna, reflector antenna, or it can be different type of antennas such as parabolic antenna. Microstimulus antenna, this patch antenna is very necessary because it has a different advantages, which are low profile, conformability, low cost fabrication,
Sir, we cannot hear you.
Hello.
Yes, sir, you are audible.
আমি শেয়ার করছি স্যার, এখন ঠিক আছে?
জি স্যার, ঠিক আছে স্যার।
পাওয়ার পয়েন্ট আচ্ছা আচ্ছা ঠিক আছে। I think my power is a bit unbalanced, so thank you for the sharing. So I'm gonna change it as per the suggestions. Okay, can you hear me now?
Yes,
Yes,
sir.
sir. Yes, sir.
Okay, good. So high gain antennas. So actually, this has been we have been developed the product on 2009. So this is our high gain antenna, the microstrip patch, and we have the two layers, which is 79 millimeter by 29 millimeter is the patch itself, and we have the ground plane. And here we have been developed with a triple EEE shape patch antenna with a L prop feeding. So we have designed in such a way that we can enhance the gain. So hence we have developed with a gain enhanced antenna. So if you look upon the product itself, that the left photo is the invented patch, and the right one is that we have developed the fabrication, and we have developed for the frequency from for IMT 200, which is from 1.8 to 2.22 gigahertz. And when you move to the return loss, we have found that the good matching device for the motion measurement. We have found the simulate is 21.79%, and the measured result is 21.15% from 1.86 to 2.3 gigahertz. We have seen the gain of the measured device. We have got pretty good gain for 9.5 dBi in the frequency of 2.0. The efficiency we got average of 80%. Then we see the radiation, measure the radiation patterns. So we can see the different frequencies 1.8, 2, and 2.18. Radiation patterns are quite good. It's just slightly directional to the left due to the profiting of L. But it's a pretty good. We got a pretty good result. And for then we move to the wideband antenna. So this had been also published in 2009. So at the last one, we had the problem that we couldn't solve to enhance the bandwidth. So here we have tried to enhance the bandwidth itself. We want to static the gain, but we want to enhance the bandwidth. So we try to implement the patch itself to give more energy to the E area. So hence we have developed and we get a better measured result of 30%, which is 1.76 to 2.38 gigahertz, and the matching was very good from the simulation and measured through the VNA. We got the gain. We got the gain, which is also above 2.1, is 9.4 dBi, and the efficiency we got around average of 72%. The radiation pattern we have developed, that we also got a pretty good radiation pattern. So you can see, although it should be 0 on the 0 degree, but slightly move to the left or right, but the way it radiated, slightly directional on the 35 degree or negative 35 degree, which shows that it's a very good base indoor base station antenna can be used. Next, we move for understanding of ultra-wideband antenna. Before we go to ultra-wideband antennas, we try to find a bit understanding of the body centric, because we're going to use the body centric, the device itself. The body centric wireless communication refers to the human self or human-to-human networking with the use of wearable and implantable wireless sensor. It is a wireless sensor network, wireless power area network, and the application including power health, personal health, smart home, can be for the entertainment purpose. It can be also for space or military purpose. In body-centric communication, antennas are the essential part of the body-centric wireless communication. And the complexity depends on the radio transceiver that require the surrounding the environment. Hence, it's the antenna is become a very crucial part in the developing the communication for the body-centric wireless communication. And we don't need to follow the IEEE 802.15, means that for the body area network, our power also need to be very low. Imagine the concept here for the body-centric network. So let's say if we can see here the different nodes are surrounding with the body, and we can see from the nodes the signal will be transformed to the PDA. From the PDA, the signal will be transformed to the network, and from the network, it will move to the either healthcare service or to the physicians. Whichever it needs to flow, it will be flown as per the requirement for getting the signals. For example, if it is a vital signal for the old people, then maybe it will change and it will send directly, the emergency response team will come directly to the patients and deliver whatever the things are necessary. So this is the big concept that for the last few years, our designers were trying to communicate with the devices, how we're gonna change the world, and how from the wireless sleep we can move to the body, so that the humans can get direct help from this amazing device. And I should want to say, well, I just want to say one thing. I mean, I should please be thankful to us, those who are behind this very tremendous work. And the mobile you have, the very significant thing is antenna itself. So I would like to say that we should be thankful to the antenna designer community. Those have changed and helped the world to be connected anytime, anywhere, any place. So now if you see the wireless personal area network and the wireless body area network, so you can see the surrounding circle from the outside. That's the wireless personal area network. Then closely is the wireless body area network. And you can see the yellow color, the nodes are connecting inside on the body. For this, like a viable sensor. It's like interly connecting, trying to get connected. And when it's off body, you connect from the PDA to the off body outside links. So what it's trying to do is like whatever the devices will be wired. So they're trying to get connected with the outside PDA to the communication, so that we can change the data whatever the required, and we can read, we can understand the signals, and we can get the signals, and whatever the signal response team need to be required can get immediate feedback from the imaging device. Let's go more understanding, so we can see about the on body, in body, and on a body. So let's say for the sports performance monitoring. So let's see like the guy having a different nodes and he's running, and with him is the base unit is there, or I just noted here. So what about the pulses or the oxygen levels, heart levels, what about the rates are there? It can get connected with the body one base unit. So from the base unit can be sent to the local transmission. Again, if we see about the in-body applications, when you see the in-body applications, the device should be inside the body, and how it's going to be connected with the outside world. So the slightly outside the body, one pulsing unit will be just slightly outside the body. So from inside to outside, it will be connected, get the response, and send back to the hospital. So that is the off box, and on the right side figure, you can see a very good figure that it shows in the dark black color is like a small base unit. So that's the fundamental thing that we should be thankful, because this is now the modern PDA that's going to help to be connected with the surrounding network. So now in concept, we can say that, so connecting with the nodes to the base station, the local PDA, then from us, and then it moves to the network, and then it moves to the hospital or the required physicians that they're handling with the patients. So for this purpose, we can categorize in off-body communication, on-body, and in-body. Or when you say off-body is human to human, on-body is the on-body network with the wearable system, and in-body is with implant device and sensors which are directly linked. So when you see the phenomena of the on-off and in-body, so let's see the cross-section. If we make the human body and cross-sect, we can see the off-body is linking to the outside. When it's in-body in the red color, is like internally linked on the surface bodies inside. And when it's on-body, let's say on the hand, it's like connecting with different nodes trying to get connected onwards. So now for understanding, so because sometimes we need the high data. For the high data, we need to see which device can be implemented. Well, UWB is a very significant device, can be used because UWB can process the high data. So why you need the UWB? Can have wide bandwidth, low power consumption, low interference, high data transmission, high speed, and definitely this is a very low cost. So let's look about the UWB technologies. So this technology offers the transmission in high data rate signals, low portability, short range wireless connections, high resolution for radar imaging. For example, if we see that wideband, the range it can give from 3.1 to frequency can operate 3.1 to 10.6 gigahertz. Pretty good wide frequency it can cover. The data rate is like 110 millimeter is Mbps. So the range can cover up to 10 meters. It's a low power, negative 10 dBm per megahertz. And you can see when you say about 3.1 to 10.6, that means it's more than 500 megahertz. That means we can have a tremendous good amount of frequency operation bandwidth. On the below photo, you can see that clearly the slightly portion it can shows that how big UWB can be, which around 7.5 gigahertz. That is pretty good actually. So with keeping this in mind, we try to go do our understanding and try to develop the antennas. Then again, about the other particular service, the WMTS, that the frequency range is 1427 to 1432 megahertz. Basically, this frequency we have been used, is certified from IEEE for the monitoring the special healthcare purpose, and also for surgical to get connected with the stations. Well, now we try to discuss about some of our works of the antennas, which are now in ultrawideband antennas. So here, a pretty good antenna you can see was already published in IEEE in 2015. On the amazing thing that the antenna is very compact. It's 15 by 17 by 10 millimeter cube. You can see it's very smaller than a coin of 50 cents. And you can see the left figures, the angularly development of folded patch feed, the benchmark of the design. In such a way, it reduced the construction areas. And on the right side of the figure, you can see the reflection of simulation measure results. And you can see that about 3.1 to 10.3 gigahertz, which is 107% bandwidth cover for this significance. Now, if we see about the recurrent distribution on the figures, just I want to say about the second figure of we can see look at the second figure. We can see a tremendous current excite on the folding area shows that the distribution is very good on this area. Help us to enhance the bandwidth to make it ultra wideband. And we see the magnitudes and group delay. These are perfectly very stable. On the right side, you can see the radiation patterns of the device. Of this device, you can see that we have a good matching the radiation patterns is not fully omnidirectional, but we can say that since it's both directional, so I think we thought that it's quite good for us to go through for publication. And we found that it was already they say it's pretty good. Then we see the sensitivity of the device. We also analyzed the gain. We found that there's a quite good matching. So it's a very good matching device we have been developed and published in IEEE. And then there's another suspense ultrawideband antenna. We also published in this one in 2015. And the mechanism we have developed is the suspenses. We can say, why don't we just give some suspenses rather than just connected? The concept of giving the suspenses and with it, giving the coupling in between had changed and enhanced the bandwidth. And we also can see the right side of the photos and also get a better understanding of radiation. And also get antenna size is very small. It's 9 by 13 by 6.7. It's very small antenna, and we can give an enormous ultrawideband to be used in the field of communication. So you can see the radiation patterns. You can see the reflection coefficient of VSWR is a pretty good matching of our proposed device. And also you can see the current distributions and different frequencies 5, 8, and 10 gigahertz. This is pretty good. And also you can see this, if we see the figure 2, very nice. And the radiation is very good, you can find. And also the other matchings, group delays are quite well. There's the sensitivity, you can also observe, we get very good, nice sensitivities. However, then we said, why don't we move from patch to planes? And we moved to have a device in patch antennas. So this is our patch antenna for 16 by 20 by 1.6. And we found that also this is the new architecture. This architecture helps us to get with this angularly shape, we enhance the bandwidth and get a very tremendous bandwidth can achieve through the frequencies. We can find our paper, this one in 2015 is USA based paper. So this the proposed system. So when you don't have the arc, we say that we give the name is arc. When you don't have the arc portion, this portion on the arc side, we need to check and we need to calculate. Without the arc, we saw that the bandwidth goes down, it gets reduced. But when you keep the arc, that we excite the current more, and hence we found the ability that why if you give using a portion of a radius of arc, we can use and enhance the band, and that's why we enhance the band. Then we said, well, we see the other parameters. So we found it's pretty. We got a very good size of device, is 16 millimeter by 20 millimeter, and the bandwidth we achieve is 96.2%. The range from 4.8 to 13.7 gigahertz. Then we found that we know that why don't we see the sensitivity? We found it's a pretty stable, and we can get a good balanced device for our product. Then we found that if we have a wideband, so we know that there is some, some of the bands like wireless, the WN band is disturbing. So why don't we just try to reject we try to design in such a way that we can reject the band of the WN. So we're using a tuning fork shell. The tuning fork has designed in such a way it rejects the band frequency on WLAN. So when if we see this is the tuning fork we have been used inside the patch, and hence it improved the frequencies. So here you can see the notches. So on the frequencies that without the band of the notch, and with the notch you can see directly there can be changes. So now we see the sensitivity of different parameters. We found that it's also good enough to understand that. The interesting part is the current distribution. If you see that this portion of the current distribution on the front figure, you can see the notch because of this notch, and on the right side you can see the group delay. It directly you can see easily that the portion which is already been removed from the frequency of UWB. Well, why am I? Okay, now we move to the off-body antenna. So this is our off-body antenna. So we're going to discuss it now. So now for the body-centric communication, if we say categorize the three domain, I know it's pretty I think might be getting bored, so that's why I'm trying to try to highlight some of the points that maybe which portion we are, so that okay, the time is not that much, yeah. So that's why we're just trying to highlight which portion, yeah. So we are in the off-body antenna now, so we can just go and see, just to have some couple of understanding of the off-body. So body-centric communication for the off-body communication, on-body and in-body. So when you go to the off-body mode, we can see the lobe is moving towards the outside, towards the 0 degree. And when we do the on-body, the lobe is surrounding us. Full lobe, if you see the black color, if you're assuming the black color is a human, so when it's on-body, the radiation itself is surrounding the body itself. So for that, how to do that, we said, okay, since we need a human body, so what can we do? Then why don't we develop the phantom? So then we develop the phantom based on the development of muscle. So we then, using the biological equivalency, we develop the phantom. This is our muscle equivalent phantom that we have been developed. So then we see the permittivity and permeability according to that. So now for the off-body mode communication, we have designed with the tri-band antennas, which will be covering for WiMAX, C and WLAN, and the upper UWB. So when we say about the upper UWB, we know that the frequency is about the 6 to 10 gigahertz. And when you say about the WLAN, is on the 5 gigahertz. And when you say about the WiMAX, we can say it is between around 3.3 to 3.7 gigahertz. So with keeping this in mind, we design, and we have developed our product. This has been published in IEEE in 2017. As you can see from the figure on left side, we have made a double ring, like a land dog. So the inner land dog and outer land dog we kept in such a way that it can balance the device and can have the optimum values of the results. On the right side, we kept on the slightly upper position of the antenna, slightly upper to the skin, fat, and muscle, and we also get the result for that purpose, and we see that we get a very good balancing device and also balancing results. You can see the current distribution and different frequencies, 3.8, 5, or 7 gigahertz. Also, you can see that we have the balancing device. And we can discuss and find in the. There's one interesting thing that need to be highlighted. When in the left photos, all the left photos you can see, this is very interesting. When it's off body, like we don't use the muscles equivalency with the device, we can see that we get omnidirectional. But whenever we put the antenna, it moves to the slightly to the directional, and the below lobes are trying to be tense to go upwards, meaning that due to the muscle, it suppressed, and the radiation has been changed slightly, moves towards the 0 dB. So this is very good finding from our this design and also developments. We also see the free space. Also, we can see the antennas for free space gain variations. We also see the antennas for the on-body, and also we see the efficiencies. Efficiency also drop on the on-body because due to the fact that we use the muscle. Now I want to show you about the on-body. So on-body, this one, for the on-body communication, this is the ultra-wideband antenna with the 1-layer phantom and with the 3-layer phantom. With that, we can we have been designed with the textile. I will not show more detail of the device because that one has not published yet, so will not go detail. So this one, only the antenna itself with the on-body, you can see that it can be worked successfully for the band of for 3 to 10.6 gigahertz, which is for the ultra wideband in properly used. This is the radiation, this is the current distribution for the different frequencies. You can see, as you can observe how balancing the kind directivity and kind distribution is working on the positions of 4.5, 8, and 10 gigahertz. I'll not show more details of the radiations because just want to show you the kind distributions. Well, now I'm going to show you the interesting part, which also we have gone through a different dimensions like high gain, we go wearable, then we go UWB, on body. Then we say, well, why don't we try to go to go inside the body? So if we want to work with the inside body, we cannot work directly to the human. That's what is the only option we have. We have the only option that we need to go through the rat or any live animal. We found that rat would be the very good animal to be take as a subject for this investigation, and hence we try to go through and communicate with the medical team, communicate with the biomedical team, animal house, animal physics. Then we found that at the end they give us the permission to go through and to work for the rat in vivo analysis. So the challenging part in body antenna communication, the patch size need to be reduced because it's a rat. It need to be low volume, and it should be the resonance should be a matching device, because if there's no matching, there's useless to be used. We need to consider the adaptability of the lossy environment. We also need to be biocompatible. So these are the lot of challenges that we need to highlight. So we will highlight this thing, we keep this mind, we try to solve, we set all, then we discover that we can do it and try to overcome this challenge. For that, we have taken the wireless medical telemetry service frequency range we have been chosen, because that's the given frequency from the IEEE workbench. The benchmark frequency is okay, can work 1.27 to 1.32. This megahertz we can work. So we try to take this frequency our target point. So for that purpose, we have the workflow. So we say rat is used as a subject for in-body mode analysis, new implantable antenna design and testing for in vivo analysis. The measurement is conducted in animal experimental unit in the Faculty of Medicine, University of Malaya, Malaysia. We collaborate this work with Faculty of Medicine, Faculty Department of Biomedical, and also our Faculty of Electricals. That the time or in Malaysia that we have been propagated. Well, the workflow can see that here the in vivo. So we took the selection of the rats, then we took the anesthetized rat, then we record the diameter of the length, make the wound of the length to 20 millimeter on the subcutaneous tissue, and then we close the wound. Then we go through the collected the through the coaxial. We check the signal response, then remove out the rat, and then we move to directly we take the signal. Then for cross section, we take the tissues from there to do the slicing and to find the cells and tissues, how the behavior and how is the stress level. Then we send to the carcass and place it to the animal house. So this is our animal house that I was working. So I think, can you see me? I'm not sure with the mask whether you can recognize me or not. I hope you still can recognize me well. With the slight beard on the right side, you can see. Okay, anyway, so this is the animal house that we need to feed the SD rat time to time, and it's like every day we need to go and feed them, and we can keep 3 rat per case. The environment need to be balanced, and the temperature should be 80 to 21 degrees centigrade. Humidity should be day and night 12 hours into balance. So with all these things we have done through in the animal house in the Faculty of Medicine, University of Malaya. So we breed the rat from his baby to born. After born, from baby we buy actually while it was baby. Then we breed it till it's like 470, 400 around 500 gram to make sure that we have enough healthy rat to be investigated. So once we got around 500 grams, so our muscle or skin got a bit thicker, so it's like we can get try to get easy for us to get mimic of the humans. So why is there? And we try many places. We found that the rat is very naughty and very disturbed. When you put on the abdomen, he just throw it out. Very stressful. Try to bite. Then we found a place on the dorsal area. On the top of the side left photo or top photo, that's the area we found. When you put there, the rats cannot touch that one. Even though it's like itchy, when you keep it for like 7 days, it becomes itchy, but they cannot touch it. So the device can be kept remain. The position we can see on the right side below the hypodermis, just on the red color I put. And we used to emphasize with the ketamine and gelatin as a combination. I will not tell the combination because this is very sensitive. The combination we use for exercise the rat for a particularly work for the field. Well, this is the device for that we have been invented. Then we have fabricated and we try to put and make it biocompatible and frequency which 10 megahertz, and that is the frequency or targeted for the device. Then we have been get the device to be work on that special frequencies, and hence we get the simulation result as well as we found the measured results. So since the measured results are below 10 dB, so we found that is a good. That's the best result for this we can got. We found it's quite good enough for our understanding. And there's the right side is you can see the kind distribution of the device. You can see it's a Mendel patch. It's very concentrated on the kind distribution. Help us to be improved and get the kind distribution matched with the resonance. Well, we do the histological slices of the rat tissue. So we cross-sect the slice. We cross-sect the area where we have kept the device. On the left, two photos you can see A and B. One is with the control mode. That means we just switch it, but there's no device. Then the second, you can for figure you can see there's a cavity. Cavity shows that the device is inside there. And this you can see it from the light microscope. This is we stain the slice. This is after 0. This is on the 2 different rats. We keep a sample of 6. It's the one we both slotted this one. Not slotted. We have to use the ketamine gelatin to sacrifice the rat and then see the subject how is the behavior. So then we experiment the 7 days we keep, then we bring it out and see whatever the things that happen. So on the right side, you can see again the figure A with the control group and in the figure B with the experimental group. So both group we can see the slices that the stress level is not that insignificant. That means this is significantly well to be used. There's no stress level that to be worried. So these are some of the photos. So we have also seen this is the liver. We also see the kidney and others. Also we found that the response is well. There's no and as per medical, this is satisfactory. So these are the some of the works that we have been highlighted. So at the end of the conclusion, we can say that different compact antennas are developed and measured for wireless communication, including polycentric communications. For in-vivo communications, we use the WMTS band with where the SD rat is being used as a live tissue. Measurements are conducted to validate the work, and the parameter studies kind distributions are performed to investigate the performance of the device. So these are the conclusion of the work. Some of the works we are doing now, which are mostly on the we are moving towards to further enhancing, like moving towards to 5G. We are moving towards to 28 gigahertz. Even we already touch upon the 60 gigahertz to investigate the millimeter wave response of our different devices. And also we are moving from we work on the RF to DC, how we can harvest the energy from radio frequency and convert to DC. We're also working this works, but these are all under working in progress. So since that's not fully complete, I'm not showing here, only showed which are already complete and published. Ethical approval. So for this, we have to conduct the animal investigation. We have the animal care. We say ISCUC. United States, they have given us the certified to do. So that's why we need to do properly as per their requirement. And for that purpose, we need to collaborate with a lot of teams. And for all the work what I am showing here today, I would like to thank a lot of universities in like University of Malaya, University of Kabangsang, Malaysia, then University of Malaysia, Pahang, then China, Chiba University in Japan. And if I say about the names, in Kaus University in Saudi Arabia, in Oman, and then universities in UK, some of the universities in UK, even in Australia. So a lot of people are involved in our giving us our suggestions, also collaborations, and also even from Iraq, also they give some of the feedback for our works. So I would like to acknowledge them all. I would like to thank all for our effort to team to be successful to be come up to this area. So for our teams, these are the works that we have been come so far. So we have got 7 patents. We got special awards of 6 special awards, 1 book, 8 awards, 18 awards, and 51 publications. Collaborators, my previous students, current students, and whoever help us to come up to this level. So the guru of our areas of mathematics, I should like to say his response: imagination is more important than knowledge. Knowledge is limited, but imagination encircles the world. If we can imagine more and more, we can change the world by research, by investigating in all of the fields. We can change the world from today to tomorrow better way. So these are some of the gurus I met. So Chang, Mr. Chang on the first photo. Chang, he is from Taiwan. This is like the guru. I don't know who is working. Definitely you know Prof. Rahmasami. So he is the giant killer of this field of electromagnetic antenna propagation. I was very fortunate and blessed to meet with him in one of the conference. He was very, very cherished person, very humble. And for this, the people like them, they actually change the concept of our field in the electromagnetic fields, as well as antennas and the propagations. So I would like to say thank you to the Maxwell, followed by the Einsteins and their next generation from Rahmasami, Raj Mitra, and those who are with the teams and working this tremendous work in the field to change the world to be better today to tomorrow, and changing the world better to be anywhere, anytime, any place. So last but not least, so I want to sum up with the quote: stay hungry, stay foolish. Thank you so much. Stay safe.
Thank you very much, sir, for giving such a great effort and giving us such an informative session. I don't know about everyone, but I am very interested to your work. Before going to the question answer session, I would like to say something. In my understanding, this is a online now. This is a medical telemetry service where we need to send the signal from our body to some server or the receiver, right? Then we need some antennas inside the body or outside the body, and according to that, the antennas are designed to get better performance or better performance in the scattering parameters and some other frequency response and others. And according to that, the antennas were designed where we need off-body antenna that needs to be a directional antenna, and we need to propagate the signal from the muscle to the environment. So the antennas are designed accordingly, and finally the total system was applied to a rat, right? Okay, sir. So now we will move towards our question answer session. You can ask any questions related to today's topic to our honorable speaker and our students. You are welcome to ask a question our speaker in Bengali. Okay, you can ask in Bengali. Abu Raihan, please unmute yourself and ask question.
আসসালামু আলাইকুম স্যার।
ওয়ালাইকুম আসসালাম।
আমার এন্টেনার বিষয়ে একটা কোয়েশ্চেন ছিল, সেটা হচ্ছে যে আমাদের এন্টেনাতে তো সাধারণত যে সিগন্যালটা ট্রান্সমিট করি অথবা রিসিভ করি সেটা হচ্ছে একটা ইলেকট্রোম্যাগনেটিক ওয়েভ সিগন্যাল। তো কিছু সিগন্যাল আছে যেটা সরাসরি না ট্রান্সফার বা রিসিভ করে, ওটা স্যাটেলাইটের মাধ্যমে করে। তো আমার যে একটা ডিভাইস আছে সেটা আমি যদি কোথাও ট্রান্সফার করি, তো সেই ক্ষেত্রে ওই ডিভাইসটাতে যে সিগন্যালটা আমি ট্রান্সমিট করব সেটার মধ্যে যদি কোনো অবস্টাকল আসে তাহলে সেই ক্ষেত্রে সিগন্যালটা ডিসকানেক্ট হয়ে যায়, কিন্তু কেন?
যদি আপনার যদি এটা নির্ভর করবে এন্টেনা টাইপস এর উপরে। এন্টেনা তো এক একটা টাইপ আছে, যেমন omnidirectional, unidirectional। যদি আপনার বেসিক এন্টেনা হয়ে থাকে, যেমন আপনি দেখবেন এন্টেনার ক্যারেক্টারিস্টিক্সটা কি। যদি ডাইরেকশনাল এন্টেনা হয়ে থাকে, ডেফিনেটলি মনে করেন যে ডাইরেকশন যদি না থাকে, এলওএস না থাকে, লাইন অফ সাইট না থাকে, তাহলে এটা কাজ করবে না। এটা যদি আবার যদি মনে করেন যে আমাদের অনেক সময় যেমন ধরেন মনোপল এন্টেনা হয়, সেগুলো মোটামুটি omnidirectional হয়ে থাকে, সেসব এন্টেনা আপনার সহজেই ইজিলি আপনার একটা সাইট কানেক্ট হতে পারে। তো ইন দ্যাট পারপাসেস যদি আপনার কানেকশন গুলো যদি আপনি দেখবেন যে আপনি কোন টাইপের এন্টেনা ইউজ করছেন, based on your usability of the device, actually it will work. So first you need to see the data, which antenna you're going to use, how you are using. So when you see the data sheet, first try to see which antenna. Among of the characteristics, you see the radiation patterns. How is the radiations? So when you see the radiation, like for example, it's omnidirectional, then definitely should be used. Unless like we have some, because if it's short range, normally there should not be any problem. But if you have high, if it is far away, there is some losses, because we know the responses are not the case, because it changes with the distance, right? So you need to change that. You need to check the data of radiations.
স্যার, থ্যাংক ইউ।
Actually, this is a kind of, because as our Dr. Ratil said, this is there's a lot of measurement needs to do work in antennas, and that's why the field is more. We become a big community all over the world, and like we know each other. So and definitely measurement becomes the most vital issue. If I say frankly, measurement is become very difficult to get accuracy, and without the accuracy of measurement, it is very difficult to publish the works. So that's why we need a lot of effort to complete the works every times, and we are also trying to develop. Whoever the some of the faculties in Bangladesh, also we have some in different universities. We're also trying to get communicate to improve this field in Bangladesh, so there will be a high chance, a broad chance for our students in Bangladesh, so that they can get more, they can publish more. Hence, with publishing more in the level of undergraduate or masters, they can get a very good chance to get a very good universities, get a scholarship to go abroad and explore this in the field of electromagnetics and propagations. That's the thing, that the vision we are working with different universities. We are trying to work here also in Bangladesh. Also, we are getting some collaborations with different universities, like in Saudi, like Malaysia, and the UK. There's direct collaboration we are doing, so that there is no problem with the measurement. But we are trying to set up some of the measurements in Bangladesh, so that why do we need to go and be tackle out? Like if I say that India, they have in IIT, they have very good measurement systems, and our surroundings, like Dr. Ratil sir, he said he also was in Malaysia in UTM. UTM has a very good system under Prof. Tarek and Prof. Kamal, and different places they have a lot of systems. So why don't we try to develop in this field more in Bangladesh so that we can have a good measurement system? With a good measurement system, we can have a good matching devices, which can be helpful for us to get more publications, enhance developing the field of as well as developing our research career towards more better on tomorrow.
Sir, if this is possible to fabricate in the near future?
In Bangladesh, we are trying to discuss this one. We are trying, because some of the device you see is my handmade. Not all we fabricate. Some is fully handmade, 100% handmade. That's the first few I handmade directly, but the rest which are need to be have stripped. That is the we are trying to deal up with how far we can try to develop this field in our country.
Any other questions? I think there is no other question. Thank you very much, sir, for giving us your time. Thank you so much.
Thank you. Thank you. It's a pleasure to be here. Thank you so much.